The multinomial distribution has a close link with multivariate hypergeometric distribution. For the multivariate hypergeometric distribution, we had started with a population where each individual belonged to exactly one of a number of categories. Then we had drawn an SRSWOR, simple random sample without replacement. Had we used SRSWR, simple random sample with replacement, then we would have obtained the multinomial distribution. This is because in SRSWR, each draw is independent of the other draws. The probability of getting a sample from category I in any draw is obviously Ni by n, call it Pi say. Then the multinomial distribution has parameters n and P1 to Pk. The main difference with the multivariate hypergeometric is that in SRSWOR, the remaining population changes with each draw, but for SRSWR, it does not. Now, if the population size capital N is much larger than the sample size little n, then the population hardly changes due to drawing the sample, and so the multivariate hypergeometric is well approximated or approaches the multinomial distribution in the limit. Let x1 to xk have multinomial distribution with parameters n and p1 to pk. Then the probability mass function PMF is this. The similarity with the binomial PMF should be obvious. Now when k is equal to 2, we get back our familiar binomial PMF, just as in the multivariate hypergeometric case. Also, marginally, each xi follows binomial with the corresponding pi as a parameter. Now, if I take a permutation of the xi, so I just reorder the xi's in some way, then it is again multinomial with the pi's permuted accordingly. Finally, the expectation is x1 to xk n times p1 to pk, and variances are n times pi times 1 minus pi. As before, you may either use univariate binomial results for these, or you may prove them by the indicator trick. And you can derive an expression for covariance xi xj also using the same trick. The expression for covariance, by the way, is much simpler for multinomial than for multivariate hypergeometric.